Okay, hello everyone. My name is Shahar and I'm happy to present the collaborative cognitive radio demo. Now, I had the pleasure to work on this demo together with Alona Kiva and Barak Avraham. And the goal of this demo is actually to develop a real-time cognitive radio system that is based on new technologies. The system is sitting right here. Again, we show you the multiband model. We have a sparse input. The carriers, their position is unknown. I don't know where the carriers are. And we want to detect first the position of the carriers and then to actually reconstruct the entire data. So that's our solution. We take the RF input that's depicted above and we insert it into the analog card. This analog card is actually sitting right here and operating in real time. That's the card. And after the card is mixing the entire signals and dividing it into different channels, each one of them is modulated a bit differently. Then we can insert them into the low-rate ADC, which is implemented here in the NI hardware, and eventually solve the system and find out both the support of the signal and fully reconstructed data. So that's the entire diagram of our solution. We have to the left the signal generator. It's actually sitting here on the left. We have the MWC card, which is shown right here. And eventually, we sample it sub-Nyquist rate. We go from 6 gig of Nyquist rate to just 120 megahertz for each channel. The entire calculation and solving of the problem is being implemented on LabVIEW hardware. We'll also show you the collaborative setting. And without further ado, we're going to move on to the actual demo. Okay, so that's quite a busy screen, and we'll start explaining. At the top, we see the actual input. Okay, that's a real live spectrum analyzer input that's being sampled at the Nyquist rate. So that's basically like cheating, but we don't really know what's the full spectrum inside the card. At the middle part, that's the actual sub-Nyquist samples. That's what our system sees. Only the sub-Nyquist samples, so we go from 3 gig to just 60 megahertz. And at the bottom, we have the full spectrum reconstruction. We actually detect the carriers. Those are the frequency carriers here at the top, and we fully reconstruct the data. If we can move on to the next scenario, we can actually a bit stress the system. In this case, with a very low SNR, we have the entire spectrum flooded by noise, and the system can still fully detect the actual position of the carriers and reconstruct them. Okay, in our next scenario, we're going to show you it doesn't even matter the position of the carriers. They can be spread across the entire spectrum or stacked together, one beside each other. So in this case, we have 3 different inputs, 3 different carriers. Those are their frequencies. We fully detect the frequencies out of these samples, just 60 megahertz per channel, and fully reconstruct them at the bottom. Okay, the final example will show us a very nice example. We always see this example of the triangle, the rectangle that are shown in the live PowerPoint presentation. And this time, we actually generate those signals live. They're depicted here above. Their frequencies don't overlap. So when we collapse all of them into the baseband, we can see them right beside each other. That's real live input that's being broadcasted right now. And we fully detect their positions, even though they're very narrow, and fully reconstruct the data. Okay, I hope you're impressed as I am about one MWC. But in real life, one MWC is not enough. We're going to need more of that. We're going to need a network that knows how to solve the entire spectrum in an entire environment. So for this case, we will show you the collaborative setting. We have right here 2 MWCs that depict a larger network. They're going to simulate, in our case, 5 systems eventually. And exactly as we see here on the map, the transmitters are spread across in space. Each one of them has different properties. Like maybe one of them is a cell phone, one of them is a mobile base station. And That's the actual map that we're going to use. In white, we have the receivers, and in green, we have the transmitters. That's the first scenario we're going to show you. In this case, the collaborative setting isn't that good because, in theory, we would like a very we like the transmitters spread across in space and the transmitters between them. In this case, all of them are shown in one corner, and the transmitters are in the second one. We have the real input here that if we would have seen all of them in one ideal approach, it would have seen like something like this. But in practice, each one of the transmitters in turn sees a different input. So we go from this perfect ideal input into this partial image. Each one of the NWCs sees just a partial image, and we're going to do our best to find out the entire spectrum map using a centralized approach. So, okay, so that's basically each one of the CRs, it did it, bless you. Okay, each one of the CRs did its best to find out about the map he sees by itself. And we're going to try and solve this entire problem using a fusion center and the two algorithms. The first one is a hard cooperation, basically just taking all of the union of the results and trying to solve, taking the best guess possible using all of them. The second one is a soft cooperation, which uses some of the signal's sparse characteristics to give a better approximation of the spectral image. At the bottom here, we see both the results in green of the soft cooperation and the hard cooperation in red. So we went from this ideal input that we only see partial information about it to a full spectral map that knows exactly the position of the carriers using this network. We're going to move on to the second scenario that shows us a more ideal approach. In this case, we have the receivers spread across in space. Each one is going to see a better map which has better information about the entire space, and hopefully we'll be able to show you good results of all of them together. I'm saying hopefully because everything that happens here is live. I have no guarantee it's going to work, so I'm crossing my fingers as we speak. It's important to say that fading and shadowing, as we see, it's not as simple as the input we see here that the spectrum analyzer is showing, because in addition, each one of the CRs has different fading and shadowing characteristics that makes it a lot harder. It's not just pointing out those, it's not like looking at your bare eye and looking, okay, it's this one. Remember, each one of the CRs sees only 60 megahertz of each band. It's really dense. It's one on top of each other. It's quite a hard problem to solve. Okay, so we've got results finally. And we see in this case that the soft cooperation succeeded in estimating exactly the carrier positions as seen here. That's the real support, and that's the soft cooperation. And the hard cooperation, the naive approach that just took the combination of all of the NWCs, failed. So good job, Alon and Barak, for developing the soft cooperation approach. Okay, I think that sums it up. Thank you very much.